superconductor logic for interfacing with quantum annealing system. Oh, I'm sorry that there's some announcements, so let me change. Okay, so I am Nobuyuki Yoshikawa from Yokohama National University, and here is a collaborator. One person is Dr. Takeuchi in AIST, and Professor Yamanashi in Yokohama National University, and student in our laboratory. Okay, so let me introduce today's outline of my talk. So at first, I will give you the background and the motivation of this study. And then I will introduce operation principle of the superconductor logic circuit. There's the two types of the superconducting logic. One is called single-flux quantum circuit. The other one is adiabatic flux quantum circuit. And then I will show you some current status of the superconducting logic circuit technology. Actually, our previous aim is making a digital, large-scale digital logic circuit. I will introduce about that activity, and then I will show you some application of this technology for interfacing with the quantum system. Today, I will introduce three types of the application. One is arbitrary amplitude SFQ microwave generator for qubit. Second one is a CMOS SFQ hybrid microwave generator for qubit. And third one is a AQFP readout circuit for Josephson parametric oscillator qubits. And we'll summarize at the end of my talk. Okay, so now the qubit quantum annealing processor and also quantum computing system will is become very large. Now more than 5,000 qubit is included in the annealing system, which is reported by D-Wave, and it's already commercially available. The problem in this system is that how to control this large system at very low temperature. For example, now this is a case of the gate type quantum computing system, and each qubit needs a 1 or 2 microwave line to control the qubit, and some readout microwave line. And right now, this looks okay, but if we scale up this side to the 1,000, 10,000, 100,000 qubit, the connection connection between the low temperature qubit with room temperature electronics become very, very hard. So to solve this problem, there are several activities. One is performed in the field of the Cryo-CMOS electronics. So Intel developed a microwave control circuit using a Cryo-CMOS. So they developed this can generate microwave pulses for controlling qubit, which can generate 8 different types of the microwave pulse with a different envelope. And they provide a microwave pulse to the more than 100 qubit. One problem is that that's energy power consumption. So now it's okay. It's around 500 milliwatt using a CMOS 22 nanometer process. But if we scale up this quantum computing scale 1,000 times, this power consumption limits the integration of the control circuit. So another promising activity is that controlling a qubit by using a SFQ pulse. I will tell you what is SFQ pulse later. They use a sharp SFQ pulse, whose width is about 2 picosecond and apply this pulse to the qubit. So by using a apply qubit, the qubit state can be changed one by one like this. So finally, they can control the qubit state like this, and they successfully get such a Rabi operation. And this is very good promising technology for controlling qubit, because these circuits can be integrated with a qubit temperature. So we can scale up this control circuit very much. One problem right now they have is the fidelity of this control to control the qubit. It's around 95%. Maybe this is coming from some dissipation of the SFQ circuit, because in each pulse generation, this pulse make some dissipation of the energy. Okay, this is our current goal for realizing all-to-all connected quantum annealing system using a Josephson parametric oscillator, JPO, which is supported by NEDO and led by Dr. Kawabe, the chairperson of this meeting. And there's many institute participate in this research project, which include AIST, NEC, and many university. And we also, our group also contribute to this project. So basic idea of this project is that we will use a Josephson parametric oscillator as a qubit. And we use a 0 and pi microwave oscillation state as a quantum state. And to get the all-to-all connection, we will use a LHC all-to-all connection scheme. And in this scheme, we have a 4-qubit unit, which have a 4-body interaction. And by placing this 4-bit system like this, we can make a all-to-all connection. So to make this system and scaling up, one idea is using a superconductor interface. So the goal in our research, our institute is making an interface circuit with these quantum annealing system. Okay, this is our basic concept to make these large-scale quantum annealing system using a JPO. So many qubit is controlled by the microwave signal, and the state of the qubit is read out by the superconducting circuit. For example, by using an AQFP circuit. I will show you the basic operation principle of the AQFP later. And even we have a many qubit, the microwave can be provided to appropriate qubit by using Dmax and max. And we can also detect a qubit state by using a MAC, using a superconducting circuit. So to realize this GPO system, we have to apply pump signal whose amplitude is gradually increased. And we also have to apply microwave signal to input to this JPO. And we also have to detect the 0 pi state of this JPO oscillation. So our goal is making these microwave generator with arbitrary amplitude and some readout circuit for detects the oscillation state, the phase of the microwave. Okay, so why we use a superconductor logic circuit? So this is a comparison of the bit energy and clock frequency of the several logic gate. So this axis is the bit energy. So if we go this way, the bit energy is very small. And this is clock period. This axis is a clock period. So if we go this way, the gate operate fast. Okay, so this is a plot for the CMOS logic. And here we have some the group of the superconductor circuit called RSFQ logic. And there's some group of the AQFP, adiabatic quantum flux parametron logic. So we have two types of the superconductor logic. One is very fast. But relatively large bit energy. And the other one is a very low energy, but a little bit slower. So we have two types of the superconductor logic at this right now. Okay. As for the AQFP logic, this is actually thermal limit of the logic operation, but by slow down the logic operation, we can make it the energy of the gate can be lower than the thermal limit, known as the Landauer limit. So this is a reversible logic gate. Okay, so there's two types of the superconductor logic. One is SFQ logic, and this is the circuit schematic of the SFQ logic. Josephson junction is connected by inductance, so we have many superconducting loop. And this circuit is DC biased, and operating speed is very fast. It's ranging 50 gigahertz, from 50 gigahertz to 100 gigahertz. And bit energy is given by IC times phi 0. IC is a critical current of the Josephson junction, and the phi 0 is a flux quantum. And this energy have to be larger than thermal energy, much larger than thermal energy given by KBT. I will tell you why it should be larger than this value later. And we have that the other type of the superconducting logic is called AQFP logic, and this is AC powered logic. And the operating speed is relatively slower than SFQ circuit, but it's still fast compared with CMOS. It's ranging from 5 gigahertz to 10 gigahertz. And the good advantage of this logic gate is bit energy is very low. It can be much lower than IC phi 0 product. Okay, so we have two types of the superconducting logic gate. And this is a circuit schematic of the SFQ logic circuit. We have many superconducting loop composed of a Josephson junction and superconducting wire. Okay, so if we apply very sharp pulse, current pulse from here, flux quantum enter to this loop. And if the LIC product of this loop is much less than phi 0, the current, rotating current exceeds this critical current. So this junction also switch. So flux quantum move to the next loop. So it propagate one by one. As a result, very sharp shaped SFQ pulse propagate like this. So the operation frequencies of this circuit is very high. In the current design, maybe 50 gigahertz clock operation is possible, and for the simple circuit, more than 100 gigahertz clock frequency is possible. Okay, so this is the potential shape of the this SFQ circuit. So the potential shape, energy shape, potential shape of the SFQ circuit is given by this washboard shaped potential, which is tilted by applying the bias current like this. So traversing the flux quantum from this loop to next loop it corresponds to the state of the this one go to the next potential minima. So during that event, there is some non-adiabatic transition, non-adiabatic energy consumption, which is given by IB times phi 0. And to reduce a spontaneous transition from here to here, this energy potential have to be much larger than thermal noise. So the energy consumption of these circuit have to be much larger than the KBT thermal noise. So this is the reason the minimum energy consumption is limited by this value, this energy in the RSFQ circuit. But we can use the adiabatic concept to reduce energy consumption of the superconducting logic gate. So this is called AQFP gate. So originally QFP gate is invented by Professor Goto in Tokyo University in 1984. And now we are developing an adiabatic version of the QFP to reduce energy consumption of the superconductor logic gate. Okay, AQFP gate is composed of a squid, which is shunted by inductance. And like this line applies excitation flux to this squid gate. And if we apply input, downward input, and if we apply excitation current, the flux enter to the left side loop. As a result, we get a large downward output. And if we apply upward input, then we apply AC excitation current. This time we get a flux in the right side. As a result, we get a large upward output. So from the small input, we can get a large output. So this is the operation principle of the AQFP gate. An important point for this adiabatic QFP is that potential change during the when we increase the excitation current, it will gradually change from single minima to the double minima like this. And there's no sudden change of the state. So we can make an adiabatic switching by using this QFP gate. Okay, so this is a potential energy of the QFP. And important parameter is the loop inductance, which is normalized like this. And output inductance, which is also normalized like this. And this is normalized excitation current and the input current. And if we increase the, in the typical parameter, if we use a typical parameter, and if we change the excitation current, you can see that we will get such a sudden transition. So this is a non-adiabatic case. But if we change the parameter, for example, so this is a loop inductance, and this is output inductance. And we also have another parameter, which is a Macamba parameter, which corresponds to the quality factor of this system. Okay, so let's think about a critically damped case. And if this loop inductance and output inductance is relatively small, you can see that if we increase the excitation current and decrease the excitation current, there is only small change, very smooth change of the phase. And you can see that this potential energy change gradually, and there's no sudden change of the system. But when these beta L and beta Q loop inductance and output inductance is relatively large, you can see that hysteresis like this and sudden change of the state. So this hysteresis induces non-adiabatic switching. So this is a case of the non-adiabatic QFP. And if we increase beta C quality factor, we can also make a adiabatic operation. The difference of these two cases is that we can make it makes the energy of this system very low. Okay, this is a bit energy versus rise time of the excitation current. So in the case of the non-adiabatic QFP, even we increase the rise time of the excitation current, there's no decrease in bit energy. But in the case of the adiabatic gate, we can decrease the bit energy as a function of the rise time. So this is a case of the adiabatic operation. And if we use an underdamped junction with a high beta C value, we can reduce a bit energy very much because the loss of the Josephson junction will be reduced. So by using this logic gate, we can make the bit energy very, very low. And even this is a Landauer limit, but we can reduce a bit energy even lower than the Landauer limit by using a high beta C adiabatic QFP gate. Okay, so now let me introduce a present status of the superconducting digital circuit technology. So in AIST, we can use two types of the superconducting IC fabrication process. One is called high-speed standard process. We call it HSDP, which is a 4-metal layer process. This is a Josephson junction. It's a niobium aluminum oxide niobium junction whose JC is 10 kiloampere per square centimeter. And we also have an advanced process. We have a 9-layer. So here we have a Josephson junction, and underneath the ground plane, we have many interconnection layers. So we can make a more high-dense integrated circuit by using this advanced process. We call it ADP process. Okay, so we already started some research, some study on these digital superconductor digital circuit using this process. And we already make a cell library, which is composed of circuit schematic and layout and some code for the digital simulation. So now we can start from some digital design, and next we can get some circuit schematic, and finally we can get a layout. So some kind of top-down design flow can be made for the RSFQ circuit and also for the AQFP circuit. So now we can use this kind of cell library to make a large-scale superconductor circuit. Okay, so this is a progress of the SFQ microprocessor or processor. And 20 years ago, we already developed a high-speed microprocessor based on SFQ circuit. So this project is collaboration with many universities in Japan. And now we can make a F50 processor. But current circuit density is quite not so good. So we can integrate maybe 20K JJ circuit on the chip. So the density of the circuit is one issue in this technology right now. As for the AQFP circuit, recently we successfully made a RISC-type microprocessor, which operate at 5 gigahertz and containing about a 20K Josephson junction. And we made some program. Program is loaded in the AQFP microprocessor, and we got a successful result for the microprocessor operation. So now the technology level status is like this. We can make a 20K level, 20K JJ level integrated circuit on the chip. Okay, so this is a comparison of the AQFP switching energy versus a state-of-art CMOS process, and we have a 5 order of magnitude advantage in terms of the switching energy. Okay, so next topics is about application of this technology for making an interface with a quantum system. So we will show 3 types of the circuit. So our aim is, so this is the current situation. Qubit is integrated in very low temperature. And our aim is making a control circuit, control and readout circuit by using a AQFP and SFQ circuit placed at the same temperature with qubit. And we can also place these AQFP, SFQ, and Cryo-CMOS circuit on the 4.2 Kelvin level temperature stage. By using these controller and readout circuit, we can make we can scale up the qubit. Okay, so for first topics is amplitude controllable microwave pulse generator using SFQ circuit. Okay, so the basic idea is like this. So from the microwave, which is applied to the superconducting circuit, we can make a SFQ pulse train in each rising edge of the microwave. So we can make a 100 gigahertz, or in this case, about 10 gigahertz SFQ pulse train is generated. Then this is split by the SFQ splitter. So we have 2 SFQ pulse train here, and we put a delay line here. The delay of each pulse train can be changed by applying the control signal applied to this delay line and combine these 2 SFQ pulse train. So as a result, after that, we will make by using a bandpass filter, we will generate a microwave signal. And if the delay or time interval between these pulse train is very small, the amplitude of the microwave will be large. And if the time difference between these 2 pulses is very large, the amplitude of the microwave will be very small. So by changing the delay of these pulse train, we can change the amplitude of the microwave signal. So this is some simulation result. By changing the control signal, we can change the microwave amplitude like this. Okay, so this is a photograph of the chip of this microwave generator. So we can switch the SFQ train, and we have a delay line here. And this is a bandpass filter with some impedance change circuit. And this is a measurement result. When we change the control current, we can change the output amplitude of the microwave signal, whose frequency is 5 gigahertz. And this is a control signal dependence, the dependence of the power on the control current. So if we increase the control current, we can increase the output power of the microwave. So by changing the control signal to the delay line, we can change the envelope of the microwave pulse. So this is one so by using this circuit, we can make a pump signal which gradually increase in the amplitude. Okay, the other idea is that we use a very high frequency SFQ shift register whose pulse density can be programmable. And this high frequency pulse train can be filtered by bandpass filter to make a arbitrary amplitude microwave pulse. And this system is, we make a many such a system, and we provide this kind of SFQ pulse train to the arbitrary qubit. And this is some simulation result. So we, this is a very high frequency SFQ pulse train whose pulse density is modulated. After we filter this SFQ train, we can get a Gaussian shaped microwave like this. So by using this technique, we can make any types of the microwave pulse. So by storing many such as the shape of the microwave, we can also use a Cryo-CMOS memory, so which store many types of the shape of the microwave signal. Okay, this is a preliminary result of the shift register, loop type shift register here. So this is a loop types SFQ flip-flop. So we will load the data to the ring types shift register. After that, we apply clock frequency, clock from here, whose frequency is around 100 gigahertz. Then we get a SFQ pulse train from here. And this is a photograph of the circular shift register, and this is a clock generator. And this is a preliminary test result. So this figure shows a bias margin operating region of this circuit as a function of frequency. And this is a simulation result. You can see that if we increase the frequency, operation region is gradually smaller, but even at higher frequency, higher than 100 gigahertz, the circuit still operate. And this is a test result. Unfortunately, the operation of the clock frequency, the clock generator is very bad this time. So we have two clock generator, fast one and slow one. And unfortunately, the frequency was limited by the clock generator this time. So I hope that in the next tape out, we can get better result. Another topics is about AQFP readout circuit. So this is Josephson parametric oscillator. And our idea is that we will detect the phase of the microwave from the GPO by using an AQFP buffer, AQFP gate. So basic idea is like this. So this is input, output from the JPO. This is very small signal. And this is the excitation line current for this AQFP gate. So this input signal and the excitation current is in phase. So we get the output 1. And if the input and the excitation current are out of the phase, we get 0. So if when the input signal amplitude is very small, due to the thermal noise, maybe we will get a 1 or 0 randomly. But if we integrate these 1 and 0, we can get clearly we get output value. So we make some integration by using a low pass filter in between these AQFP buffer gate. So the signal is arriving here, input from here and integrate it by this low-pass filter. And we can also do some digital integration for the output from this signal. And this is a microphotograph of these AQFP readout circuit. So this one is a AQFP logic gate, and low-pass filter is inserted here, and we get the output signal. This output driver to amplify the small signal to detect room temperature electronics. And this is output readout characteristics. This is phase difference of the input microwave. And this is amplitude of the input current. From this figure, we can see this red one is correspond to the 1, and this one correspond to the 0. We can clearly distinguish 0 and pi state by using this technique. And from the simulation, input sensitivity is less than 0.1 microampere, but right now experimental result is worse than the simulation result. And now we are investigating to improve the sensitivity of this circuit. Okay, so now it's time to finish. I'm sorry that I was late. And it was shown that superconductor interface are promising technology for quantum computers. And we introduce latest research of the interface circuit for the superconductor circuit. And as a following step, now we are developing an AQFP microwave generator whose energy consumption is very, very low. And now we are planning to make a connection between the interface circuit and qubit. Okay, thank you for your attention.
Thank you very much, Yoshikawa sensei. So it's very wonderful and very interesting result and technology. So now the seminar is open for discussion and question. If you have a question, please use raise hand button in your screen, or just switch on your mic and give your comment or question directly. Do you have any question or comment? Hi, Paul, please. Yes.
Hello, Professor Yoshikawa. Thank you very much.
Hello.
A very nice presentation.
Thank you very much.
Yeah, Paul Wolfson here at University College London. I'm wondering, and maybe this question is a little crazy, I don't know, but is there any advantage in fabricating your SFQ and your AQFP circuits using all aluminium technology and not using niobium at all? So number one, I guess, is that a good idea, which might allow closer integration with the qubits?
Oh, okay. I understand your question. And advantage using a niobium junction is a large energy gap. So we can increase frequency, operation frequency of the gate. So for example, for the SFQ gate, operation frequency is more than 100 gigahertz. If we make it by using an aluminum junction, operation frequency become very, very low. So I don't know, in this case, we have advantage or not. One good point is that we can operate at the same temperature with a qubit. But in terms of for the digital operation, the operation frequency become very low. So good idea is we make a qubit by using an aluminum junction, and we make the digital circuit by using a niobium junction, and we put together by using some flip chip or some technology. So this is a good idea. And as for the AQFP, the reduction of the energy coming from the the ratio of the internal switching speed with the operation speed. So if we use the aluminum junction, it means that the internal operations, characteristic operation speed will be reduced. It means that we also lose the advantage of the low energy. So we have to slow down to reduce the energy. So anyway, my opinion is that maybe flip chip or making a chip in the different chip and get together by using some flip chip or some technology is a good idea. But I'm not sure. Maybe aluminum, if we make an aluminum SFQ circuit, I didn't think about that approach. So maybe we should think about more careful about that idea.
Thank you very much for your answer. I see in the chat there's a question from David Ferguson. Shiro?
Yes, David. Yes, actually, David gave a question in chat. Can you directly switch on your mic and the microphone and give a question directly?
Hello.
If you can. Okay, please, David. Yes.
Yeah.
Yes. Good.
Great. Thanks very much for the talk. You mentioned integration with JPOs, which would enable many different technologies, but in particular, JPO style annealers. Are you also considering AQFP type control with a D-Wave style annealer?
Oh, at this moment, we concentrated on JPO quantum annealer because this is a project. So our aim is making a control circuit and readout circuit for JPO types quantum annealer. But our goal is making a control circuit and readout circuit for the gate-typed qubit. So this is a second aim in our project. So we are thinking about that controller and also a readout circuit for the gate-type qubit, like yeah.
Great, thank you.
Okay, so any other question, comment? Okay, if not, so let's close today's INQA seminar and let's thanks to the Yoshikawa sensei again. Thank you very much. Yes, very great, nice talk. So,
thank you.
Okay, so so Shanice, do you have any announcement or Paul? Do you have any announcement or something?
Yeah, sure. Let me just remind people on the call that the deadline for abstracts in conference is at the end of this week. So check your emails coming from INQA. Follow the link for abstract submission, and we look forward to receiving your abstracts this week if possible. Thank you very much, Shiro.
Okay, thank you very much. So see you next. Bye.
Bye-bye.
Bye-bye. Okay.